Today we're going to talk about what's called optimization problems. So we've been talking a lot this unit about finding local maxima and finding local minima or absolute maxima and minima. And what we're going to do now is we're going to start to apply that idea to some real world situations. So if we're going to optimize something, it means we're going to be looking for the maximum or the minimum value. It might be a minimum cost or a maximum profit or a maximum volume. So there's going to be a few steps in here that are going to be pretty important for us as we work through, and things that we kind of need to think about as we're doing optimization problems. One is you got to read the problem. And if you don't read the problem and understand what's being asked of you, there's no way you're going to be able to solve it. Almost all the time, a picture is going to be useful to us. So try and draw a picture of the situation we're looking at it, and label it with whatever variables are appropriate. Then we're going to write an equation that's relating all of the information given to us, including the thing that we're trying to maximize or minimize. And once we have that equation, think about the domain for it that makes sense in the context of the problem. So we'll see a couple examples of what that means in a little bit. And then once you've determined which variable is to be maximized or minimized, make sure you write your equation as a function of that variable. Then we're going to just look for a derivative of our equation. We'll calculate the critical values of it because that'll be where we could have a max or a min. And then we'll figure out which of those possible locations of the max and min actually yields the maximum or minimum by checking the critical values. And if it's a closed interval, remembering that we'll also need to always check the endpoints. So let's take a quick look at a few optimization problems. So we're going to start off with a fairly straightforward one. We're going to try and find the point on the graph of y equals x squared plus 1 that is closest to the point 3, 1. So the first thing that we're going to do is think about what this means. Well, we're talking about a function, x squared plus 1, a parabola. And then we're talking about another point, the point 3, 1, which if we were to try to plug 3 into this equation, we'd see that the 310 is on our parabola. So the point 3, 1 is not on our parabola. So we're talking about when is the distance between that parabola and that point at a minimum. So the first thing we'll want to do is, well, draw that picture. Here's a just pretty crude sketch of what y equals x squared plus 1 looks like. We should know what y equals x squared plus 1 looks like. It's just a parabola that's been shifted up 1 unit. So here's y equals x squared plus 1. And then we're talking about the point 3, 1. Okay? And so we're saying somewhere along this parabola, right, somewhere coming across here, the distance from this point, and I'm going to draw this distance that I've drawn here in red, is at a minimum, right? There's lots of different ways we could draw this distance over here, up here. One of them is the smallest distance. So what we need to do then is we need to think about a generic formula that's going to represent the distance between this point 3, 1 and this function y equals x squared plus 1. When we're talking about distance in a coordinate plane, we usually want to use the distance formula. So just to remind ourselves, the distance formula is distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared, right? This is just the Pythagorean theorem converted into the distance formula. So we need 2 points in order to write this equation. So one of those points, I think pretty obviously, is going to be the point 3, 1. And the other one will just be some generic point here, x, the y value on that parabola, or x squared plus 1. So we're going to write a distance formula equation using those 2 points. So our distance will be the square root of x2. Let's start with just x here as our x2. So we'll do x minus 3 squared, and then plus our y2, well, that's going to be x squared plus 1. So x squared plus 1 minus our second y value, 1 squared. So simplified down, our distance formula is going to be a square root of x minus 3 squared is x squared minus 6x plus 9 plus x squared squared is x to the 4. So we've got a nice little formula here that's going to represent the distance between those 2 points. And now, if we look back at our list there of things that we need to do, we've read the problem, we've understood, we've drawn a picture and labeled it. We've written an equation. We haven't really determined the domain of it that makes sense in our equation, which we'll take care of that in just a second here. And I think we do sort of know which variable we need to maximize or minimize. Right? We want to minimize our distance. So in terms of the domain of this that matters, really the value of x could be anything, right? Because we could have any x value that gets plugged into this distance formula should give us an actual distance in the coordinate plane here. And we know that this distance is never going to equal 0 for 1 because our point's not actually on the ground. So we're up to step 5 here. Right? Domain here is all real numbers. Any point could be the minimum distance. Obviously, there's some like way over here. That's not going to be the minimum distance. But we can plug any x value into this and see what we get. So let's find our derivative. So our derivative, d prime, well, this is just a pretty straightforward radical function. So it's 1 over 2 root x squared minus 6x plus 9 plus x to the 4th. And in the numerator, we'll get the derivative of what's inside the radical. I'll put this 4x cubed term from the x to the 4th first, and then plus 2x minus 6. And first, we're going to note that d prime is only undefined for any values that make x squared minus 6x plus 9 plus x to the 4th equal to 0. And there aren't any values that make that equal to 0. I think that's pretty obvious to see. We already said that that distance is never going to be equal to 0. And that's the same thing that's inside of our square root on our distance formula. So we could say that's never true. And so d prime only equals 0 if the numerator, 4x cubed plus 2x minus 6 equals 0. So what we're going to do now is we're going to try and solve that cubical equation. So we've got 4x cubed plus 2x minus 6 equals 0. And so our first step is, well, makes sense to factor out the 2 from all of it, just so it's a little bit easier to deal with. So let's do that. We got 2 times 2x cubed plus x minus 3 is equal to 0. And we still have a cubic to deal with, which means we're going to need to, well, in this case, use the rational root theorem, because that can't be factored by grouping. So the rational root theorem says, take the factors of the constant. So factors of -3 are positive or -1 and positive or -3. And the factors of the leading coefficient, 2, positive or -1 and positive or -2. And then just divide each set by each of the other values. So we could end up with positive or -1 divided by positive or -1, which would yield positive or -1. Or the 1 divided by the 2 would give us positive or -1/2. The 3 divided by the 1 would give us positive or -3. And the 3 divided by the 2 would give us positive or -3/2. And from there, it's unless you want to use Descartes' rule of sign, which I'm not going to worry about, we're just going to pick one of these values to start with and divide our cubic by the binomial that would make one of these values our root. So let's start with x equals 1. as a first attempt here. So we can use synthetic division because we're just dividing by a binomial x minus a. So we'll put the 1 up in a box in the top, and then we'll put out our leading coefficient first. So in this case, it's a 2. And we don't have an x squared term, so we'll put a 0 for that. We have 1x and a constant of -3. And synthetic division says drop this first number down below the line, and then multiply by the number that's in the box. So 1 times 2 is 2. Put it in the next column. When we've got 2 numbers up above the line, we'll add them. And then since we have a number below, now we'll again multiply it by what we put up in our box here, this 1, making another 2. We'll add the 1 and the 2 to give us 3. We'll multiply the 1 that's up in that box by 3 to give us 3. And we'll add those, which gives us 0. And we got lucky here on our first try that this seems to have factored using x minus 1 as a factor, giving us x equals 1 as a root. So this factored into, we'll keep the 2 that we had, 2 times x minus 1. And then this gives us the coefficients of our quadratic. It's a quadratic because we were a cubic, and we've broken it down by a power of 1. We've dropped the power by 1. So we've got 2x squared plus 2x plus 3 is equal to 0. Well, x minus 1 gives us x equals 1. And 2x squared plus 2x plus 3, well, we can think back to algebra 1, the discriminant, b squared minus 4ac. Well, that's 2 squared minus 4 times 2 times 3, which is less than 0, means that that quadratic has no real solutions. So our only possibility where we might end up having a maximum or possibly a minimum, we're hoping for a minimum here, is at x equals 1. And so it's very important that we then go in and prove that this is actually a minimum and not a maximum, and also prove that there's actually an extreme of it. Now, if we look back at our list of things we need to do, we needed to check the endpoints, but because our domain that we talked about was negative infinity to infinity, that's going to tell us that there are no endpoints of the domain. So really, we just need to check x equals 1. So we have a sign chart now with x equals 1. And I'll go ahead and make that sign chart here on the next page. This is for d prime. And if we look, let's see, what was our derivative? Our original derivative was 4x cubed plus 2x minus 6 over 2 times root x squared minus 6x plus 9 plus x to the 4th, right here. So if we divide all those terms in the numerator by just 2, then we've gotten the denominator. Our derivative is 2x cubed plus x minus 3 over the square root of, we had an x to the 4th plus an x squared minus a 6x plus 9. And let me just confirm that's right. Yep, that's all the right terms there. So if we plug in something more than 1 to that, let's say like, I don't know, 1,000,000, our denominator is always going to be positive. And our numerator here, 1,000,000 cubed plus 1,000,000 is going to be pretty big. Subtract 3, that's still going to be positive. So we've got a positive over a positive, telling us that our function, our distance, is increasing after x equals 1. And then if we plug in something less than 1, like 0, we're going to end up with a -3 over the square root of 9. That's a negative over a positive. And a negative over a positive yields a negative, so the function is decreasing, which tells us we must have a minimum at x equals 1. And then the question asks us at what point, if we look back here, find the point, which means we need to evaluate x squared plus 1 when x is 1. So at x equals 1, x squared plus 1 equals 1 squared is 1 plus 1 is 2. And so the minimum distance occurs at the point 1, 2. That's when the point 3, 1 is closest to that parabola line with x squared plus. In this problem, we're looking at an open top box that's being constructed by cutting congruent squares with a side length of x from the corners, the 20 by 25 inch sheet of 10. And then we're going to bend the sides up to make the box. We want to know how large the square should be in order to make the box hold as much as possible. And we want to know what is the maximum volume of this box. So I think drawing a picture is going to kind of help us understand what's going on here. We've got a rectangular shape here that is starting off 25 inches by 20 inches. Okay. And what we're going to do is we're actually going to go ahead and cut off some squares from the corners. That's what it's telling us we're doing here, cutting off some squares of some length. We don't know what length. We call it length x, and they're all the same. So this is x, and this is x, x, and x, and so on. They're all of length x. And so when we do that, we'll have removed these little pieces here, and we're left with some little flaps, right, on the sticking out from our rectangle. And those flaps are going to just be folded up right along these edges right here. Okay, we're going to fold those flaps up into a box that has no top to it. Okay? And so we're looking for how much should we cut off so that the box holds as much as possible. Well, how much a box holds is its volume. So what we need to do is we need to write an equation that's going to represent the volume of this box. Well, the volume of any box, rectangular box, is the length times the width times the height. Right? And so if we've folded up these sides, like if I fold this side up right here, so that it was sticking straight out of the screen towards you, the height of this box is going to end up just being x, right? It's just going to end up being this length right here. That'll be what's jutting out of the screen at you. That's just an x value. Okay? So one of our terms, length, width, or height, doesn't really matter what you call them, b, is going to be x times something times something else. So we'll call this one from here to here is the length. And our original length along the side was 25. But on both sides, we've cut off, and I'll do that in a different color for a second here. We've cut off x units on each side. So we've got 25 units minus 2x. So we'll have 25 minus 2x here. And similarly, or we'll call it the width, we started with 20, but we cut off x and x. So that'll be 20 minus 2x. And if we go ahead and distribute all of this together, negative 2x times a negative 2x is 4x squared. And if we multiply that by the other x, that would be 4x cubed. And then we've got a negative 2x times 20 and a negative 2x times 25. That's a negative 40 and a negative 50. So that's negative 90x. And then it's getting multiplied by another x, so negative 90x squared. And then we've got a 20 times a 25. 20 times 25 is 100. Sorry, 500. So 100, 500. And 20 times 25 is 500 times that x is plus 500x. So we've got a nice little equation for our volume of our box right here. And let's think about what the domain of this is, because that was one of the things we were supposed to be thinking about, the domain. In the context of this problem, there's some restrictions on what x could be. Now, the volume function has no restrictions itself. Right? You can plug x in for that, for any value of x. But we know that we're cutting off congruent squares here, and that our original side was a length of 20 here. So the most I could cut off, I couldn't cut off 10. I could cut off almost 10. But if I cut off 10, I've cut off the entire edge of the box right there. So that's going to tell us that x must be less than 10. And also we got to cut something, which is going to tell us that x must be greater than 0. So effectively, we are looking at a domain for x of 0 to 10. So any values we get that might be critical values, if we do get any, that are outside of the interval 0 to 10 can just be disregarded. And another thing to note is way back at the beginning, we said at the end, check the endpoints. But we'll note that this is an open interval. We got to cut something off, so we can't cut 0. We can't cut 10 because then we've cut off the whole side. So there's no endpoints, and there's no reason to check the value of 10 as a largest or a smallest value. So now we're ready to take our derivative of 4x cubed minus 90x squared plus 500x. So let's go to a new page. We got volume is equal to 4x cubed minus 90x squared plus 500x. And if we take our derivative here, v prime will be 12x squared minus 180x plus 500. And I think it's pretty obvious that that's never going to be undefined, right? V prime is never undefined. We'll write that anyway. But it does equal 0 if the whole thing equals 0. And seems like we should be able to reduce that down just a little bit. Clearly, they're all divisible by 2. I think if we divide them all by 2, we'll see that we can divide them all by 2 again. So I think we can divide them all by 4. So if we divide them all by 4, that gives us 3x squared. And then 180 divided by 4 is 45, so minus 45x. And if you divide 500 by 4, that would be 125. And we'll make sure we keep that 4 in there for now, just so we have an actual expression for v prime, even that 4 is not really going to make a difference here. And so now, well, we got to see if we can factor 3x squared minus 45x plus 125. But I think if you go through and you use the discriminant on that, you'll find that it doesn't equal a perfect square, which means that you're not going to be able to factor that cleanly. So we'll need to just go ahead and use the quadratic formula for this. So we've got x equals the opposite of v, so 45, plus or minus the square root of negative 45 squared minus 4 times a times c, all over 2 times a, or 6. And so from there, it's just some arithmetic. We've got now 45 plus or minus, and then we got to figure out what 45 squared is. 45 squared is 2025, so 2025. And then 4 times 3 is 12, so we got 12 times 125. And 12 times 125 is 1,500. So minus, I almost put a plus there, minus 1,500 all over 6. And if we do 25 minus 1,500, that ought to give us 525. So we're looking at 45 plus or minus the square root of 525 all over 6. And I think right off the bat, it's pretty obvious to see that 525 can be, that radical can be simplified, but it divides evenly by 25 really nicely. And does that 21 times 25 is 525. So this is 45 plus or minus 5 times root 21 all over 6. And that gives us 2 different critical values. And so we might need to then go in and use our graphing calculator to just approximate what those values are. Just make sure they're both between 0 and 10. So let's real quickly do that. And we'll need to have to reopen this graphing calculator here. We've got 45 plus, and let's see if I remember this right. I think it was 5 times the square root of 21. And I should have put that all into parentheses to begin with, so I'll do that now. 45 plus 5 root 21, all divided by 6. Comes out to be 11.318. That's not within our domain, so we can ignore that as a critical value. And if we do, remember my parentheses this time, 45 minus 5 root 21, all divided by 6, that's about 3.6811 and so on, which does seem to be in our domain. So we'll go back here and say that only the -1 is in our domain. Only the minus is on 0 to 10. So that's our only critical value. And so when we make our sign chart here, we will say we have 45 minus 5 root 21 over 6. And we'll put 10 and 0 at the ends of our sign chart just to remind ourselves not to pick anything in between there. And we said that that value was, let's see, what did we say? That was approximately, back at this again, 3.681186,921. So we'll put that in. That's approximately 3.681186,921. That'll give us a good idea of what to plug in to our derivative. And our derivative, once again, once we got all finished with that, was that 4 is not going to really be significant to whether the derivative is positive or negative. So I'm just going to stick with 3x squared minus 45x plus 125. I guess I should keep the 4 there, right? Since I called it b prime, so times 4. And if we evaluate something less than 3.68, like 1 in here, we've got 3 minus 45 plus 125, which is clearly positive, times 4, which is clearly positive. So our derivative is positive and we're increasing. And if we were to plug in something like 9, something between 3.68 and 10, we'd have 3 times 81 minus 45 times 3 is 135 plus 125 here. And then, of course, that's all, I'm sorry, 45 times 9, not 45 times 3. So that'd be 405 plus the 125 times the 4. And 3 times 81, that's just 243. 243 and 125 is less than 405. So this ends up being a negative number, which means we are now decreasing. So we can say that we do have a maximum volume if we cut off squares of this length. X needs to be this many, I believe our units were inches. And then it did ask us in the end here, we look back at the problem, it said, what is the maximum volume? So our original volume formula was this, x times 25 minus 2x times 20 minus 2x. And I'm going to go ahead and use the little trick that we've got here on our graphing calculator. If we evaluate this at 3.681186,921, or 45 minus 5 root 21 over 6, we'll get an actual volume. So let's do that on our graphing calculator here. Remember that we can take this value right here, 45 minus 5 root 21 divided by 6, and hit this button right above on, the STO arrow button, and store that as alpha, and then the math button A. And then I don't have to rewrite that or retype that number each and every time. I can just go in and say my volume was X, which my X is going to be A, and then 20 minus 2X, or 20 minus 2A. And then we also had 25 minus 2A. And if we hit enter on that, we end up with 820.5281926. And we can go right in here and say this was approximately equal to 820.5281926 inches cubed. And again, on the AP test or on my test, you can round to 3 decimals. So 820.528 would be acceptable, or anything more than that also is good. Here we've got a company designing a 2-liter, which is 2,000 cubic centimeters. That's an oil can in the shape of a cylinder. We want to know what dimensions in centimeters will use the least amount of material. So we're talking about a cylinder. If we're talking about a cylinder, we'll sketch a little cylinder here. Not going to be perfect, but good enough. And we know that it's got a volume of 2,000 cubic centimeters. So I'm just going to kind of put that information on the side here. Our volume has to be 2,000. We want to know what dimensions will use the least amount of material. Well, the material would be the surface area. So I'll just call that A in this case. We know that A would be the area of the circle on the top plus the area of the circle on the bottom. To start with, that'll be 2 pi times r squared, right? Pi r squared for each, the top and the bottom. And then our lateral surface area, right? The part going around all of this right here. That lateral surface area is the circumference times the height. And the circumference of this is 2 pi r. And the height is just going to be called h. So we've now got a formula for the surface area, but we've got this formula in 2 different variables, both r and h. So we've got to find a way to sort of get this into one variable. The way we're going to do that is by using this information that was given to us about the volume. We know that our volume is 2,000. And we know that volume for a cylinder should be the area of the base, pi r squared, times the height. So 2,000 needs to equal pi r squared h, where this right here is our radius, and this right here is our height. So we need to optimize this area equation, the surface area equation. But before we can do that, we need to replace this h with an r. So in order to do that, we'll take this 2,000 equals pi r squared h and say h must be equal to 2,000 divided by pi r squared. And we can go in and replace that and rewrite our surface area equation as 2 pi r squared plus 2 pi r times h, which is now 2,000 over pi r squared. And this should be simplified into the area is 2 pi r squared plus 4,000. And then we've got pi divided by pi, that ought to cancel out. And then we've got an r divided by r squared, which ought to become 1 over r, or r to the negative 1 half. So we now have a surface area formula, A equals 2 pi r squared plus 4,000 r to the negative 1, all in terms of the radius of our cylinder. And so it's now time for us to think about what the domain of this is. Now, obviously, r could be anything for this other than 0, because 4,000 r to the negative 1 is like 4,000 over r, and r clearly couldn't be 0, which makes sense anyway, because you're not going to have the radius of the cylinder be 0. In fact, the radius of a cylinder also couldn't be negative. So we're going to say this is only good for r greater than 0. So any negative values we might get can just be ignored. So now we're ready to take our derivative. A prime should be equal to, with respect to r, this derivative is 4 pi r minus 4,000 r to the negative 2 power. And we can rewrite that as 4 pi r minus 4,000 over r squared. And then when we go ahead and simplify this down, we're going to get a common denominator. We'll multiply by r squared over r squared to give us 4 pi r cubed minus 4,000 all over r squared. So we'll get a new page here and say that our a prime, our derivative of our surface area, is equal to 4 pi r cubed minus 4,000 all over r squared. And this is undefined. R equals 0, but we're going to ignore that because it wasn't in our domain that we restricted this function to. And a prime equals 0 if 4 pi r cubed minus 4,000 equals 0. A prime equals 0 if that's true. We can just solve that for r. First off, we'll add the 4,000. 4 pi r cubed equals 4,000. Divide by 4 and divide by pi gives us r cubed equals 1,000 over pi. And r is equal to 10 over the cube root of pi, since the cube root of 1,000 is 10. And let's just get an approximate value for this, just so we've got it for our sign chart. Right? We're going to need to put this value onto a sign chart. So here is, we'll put 0 as an endpoint over here, even though it's not really an endpoint. We've got 10 over the cube root of pi, which is approximately equal to, and let's take a look on our graphing calculator again, 10 divided by the cube root of pi, that's about 6.8. Of course, since this isn't the final answer, we're not going to round that. This is 6.827840,633. And if we're going to plug in something that is between 0 and that number, let's try 1 into our derivative of our surface area. If we plug in 1 up here for r, the denominator is positive. In fact, the denominator r squared is always going to be positive, so we can kind of just ignore that. But if r is 1 in the numerator, r cubed is 1, leaving us with 4 pi minus 4,000, which is clearly negative, and this function is decreasing. And if we plug in something more than 6.8, like let's say we plugged in 9, again, the denominator is going to be a positive value. Then 9 cubed is 729, right? Yeah, that's right. And from there, well, we got to multiply that by 4 pi. And I think we should be able to probably see that, I mean, if we assume 4 pi is about 12, 729 times 12 is going to be a lot more than 4,000. We're going to get a positive value there. So this is at a minimum when our radius is 10 over the cube root of pi, or 6.827840633. I think it was centimeters we were talking about here. Yeah, we have cubic centimeters, so centimeters. So we'll go back in here and call this centimeters. So that's our radius. And then we're also asked, well, it said find all the dimensions. If we go back to the beginning of what we looked at here, we know that h is equal to 2,000 over pi r squared. And so let's see, we're just going to do h for this. If h is 2000 over pi r squared, let's evaluate that when r is, what do we have here? 10 over the cube root of pi, I believe. So 10 over the cube root of pi. That's what we'll have here. That gives us 2000 over pi times 10 over the cube root of pi is pi to the 1/3. And then that value of r needs to be squared. So to simplify this down, we've got 2000 over pi times 100 over pi the 2/3. 2000 divided by 100 is just 20. And then pi over pi to the 2/3, subtract the exponents, pi to the first over pi to the 2/3 is pi to the 1/3, or the cube root of pi. This is also going to be in centimeters. And we could get a decimal approximation for that also, but if I don't ask for it, there's not really any. We got a few more of these we're going to look at here. We'll start with this. We've got a rectangle that is inscribed under one arch of the standard sine curve. And we are looking for the largest area that that rectangle could have and trying to figure out what the dimensions of that rectangle are that give us that area. So the first thing we'll do is just take a quick sketch of one arch of the sine curve. And when we talk about a rectangle being inscribed under one arch of a curve, we're talking about underneath the curve, but still adjacent to the x-axis. So a rectangle that looks something like that. Now, of course, there's a lot of generic looking rectangles that could be drawn in there, right? I could draw a taller, skinnier rectangle, or I could draw a shorter, longer rectangle, like a long rectangle that's not quite as tall. But we're just talking about any generic rectangle. So we'll just keep this one as drawn here. And we'll note that this function here is y equals sine of x. And we want the area of that rectangle to be at its maximum. So we're looking for a maximum value here as we optimize it. Well, the area of any rectangle is just, we'll call it base times height. That's all the area of a rectangle is. So really, we just need to figure out what the base and the height of this are in generic terms of x. Okay? So in order to do that, let's start by thinking about what this coordinate here is. Well, this coordinate is just the distance over on the x-axis from the origin. It's just some generic distance of x. And because that's true, this y coordinate up here should just be our function evaluated at x. So this point right here is the point x, comma, sine x. Well, right off the bat, that tells us what h is. H is the sine of x. So we're halfway there. Now we just need a value for b, the base. Because we know that a sine function is symmetric across any of its maxima or minima, right down this middle right there, it's symmetric. And this rectangle is hitting the same points, the same y values right here. We know that this distance here, well, it's not actually an x from the origin over, it has the same length as that. So this is also x. And so we can see that our b value plus 2x should equal one full length of this arch of the sine curve. And we know that this value right here must be x equals pi, because the sine of pi is equal to 0. So our value for b must end up being the full length, which is pi, minus 2 times x, telling us that the area of this rectangle in generic terms is sine x times pi minus 2x. And we'll now need to take a derivative and see when it's equal to 0. And we'll note that our domain here, well, we're cutting off x from each side here, from 0 to pi. And so we can't go more than halfway over for x. And we can't go 0 over. So our domain should be from 0, non-inclusive, to the midpoint here, which would be half of pi over 2. And since we can't go the whole way in there either, we can't cut off half of it for our rectangle. We'll call this another open interval, and we've got no endpoints that we need to change. And so now we can take our derivative. A prime should be our first function times the derivative of pi minus 2x. The derivative of pi is 0, and the derivative of negative 2x is negative 2. And then we'll add to that cosine of x, the derivative of sine, times pi minus 2x. And, well, if we look at that, that's going to be a function that's a little bit difficult for us to solve by hand. Now, we've learned Newton's method. We could approximate the root of that using Newton's method, but that's going to require a calculator a lot more work than just graphing it and using the graph calculator functionality to do that with. So we're going to graph that and see where it has an x-intercept. And we're going to note that this thing is never undefined. So we'll say a prime is never undefined. But since we would assume this question would be a graphing calculator question, we'll just say a prime equals 0 if x is approximately, and well, now we're going to go in and graph that derivative on our graphing calculator. We'll go into y equals, and we will say, well, we have sine x times negative 2, so that's negative 2 sine x. And then plus, and we had cosine x. And we had pi minus 2x. And when we graph that, we can see that we've got a couple of different places where this is crossing the x-axis. But we knew that our domain that we were talking about was 0 to pi over 2. So let's go into our window settings and make the x minimum 0 and the x maximum pi over 2. And conveniently, we can just use pi. And when we hit enter from there, it ends up converting it to a decimal approximation. But we can now see that our graph shows us the only x-intercept on that interval, which we can hit second trace and calculate option 2, 0. It says left bound, so we'll scroll to the left. So we're to the left of the x-intercept and we'll hit enter. Then we'll scroll to the right when it says right bound, so we're to the right. We'll hit enter. When it says yes, we'll hit enter again. And it will give us that approximation of 0.710462. And one other thing that we're going to note here is this is a graph of our derivative. And we can see that to the left of that value, the derivative is positive. That's going to indicate to us that this function is increasing to the left of our x value. And to the right, our derivative is negative, which means that it's going to indicate that it is decreasing after that. So let's go back in. That's going to help us with our sign chart. Our x value that we got was 0.710462. And our sign chart at 0.710462. We don't actually need to do any calculations because we already saw that on the left it was positive and on the right our derivative was negative. So our function increases and then decreases, telling us that this must be a location where we get the maximum area. And our dimensions and our area are all that's left to find. We're just going to use this x value that we've already got, 0.710462. And our height will be the sine of that number, 0.710462. And our base will be pi minus 2 times 0.710467. And the area itself will just be that b value times that h value. And we'll see what all those are on our graphing calculator here in just a second. So let's switch over to the graphing calculator again. And we'll quit out of that. And the first thing we're looking for is the sine of 0.710467, which gives us that number. And the next thing we're looking for is pi minus 2 times 0.710467, which gives us that number. And the last thing we're looking for is the area itself, which was those two numbers added together or multiplied together. If you have one of the newer graphing calculators, you can just go up and click on 0.65 and hit enter, and it will drop it down there. Then you can say times and go up and hit enter on that other one, and then just see what that value is. And if you don't have one of the newer graphing calculators, unfortunately, you're going to have to just type those numbers back out. But I'm just going to do it this way. And we'll go back in. That first value that we got was 0.6521845953 as our height. Our base was 1.72066724, and our total area was 1.122192677. That's it for that one. For this one, we're going to inscribe a cylinder into a sphere with a radius of 10 centimeters and try to find the maximum volume of that cylinder. So, in order to do that, first let's sketch out a sphere. So here is a circle, which I'm going to then turn into a sphere sort of here with my crude three-dimensional drawing. And then within there, and I'm going to use a different color just to kind of hopefully make it look a little more clear. And I'm going to use just all solid lines here, even though it's in the interior here. We've got something like this. We've got a cylinder inscribed so that the circle that makes the top and the bottom is touching along the rim, like that. The circumference of that circle is touching that sphere at all points on the circumference. And we're going to say that this sphere itself has a radius of 10 centimeters. And this kind of problem is the one where we've got to get just a little bit creative with what we're doing. So first off, we're looking for the volume of a cylinder. And again, we know how to find the volume of the cylinder, right? The volume of the cylinder, that for now, is just the area of the base times the height. So we'll deal with that in a second, how to get that all in terms of one variable. But that's what we're trying to maximize, is that volume, pi r squared h. And now we've got to find a creative way to go about doing that. And so the first thing that we'll need to do is maybe put on our picture here that this is the r value that we're looking at, and that the height we're talking about is, let's not use black, let's try something else here just to make it a little easier to see. This is the height value that we're looking at. And looking for that maximum volume using that radius of 10 centimeters for the sphere. So that's all the information that we're given here. So we're going to have to be a little creative about what we can do. And one thing we'll need to notice is that the radius of that sphere goes from the center of the sphere to any point on the outside of it. So I could draw that, for example, to right here also, and that would also be 10 centimeters. And what we would hopefully note then is that that makes a nice little right triangle here, using R as one of our leg lengths. And so this value here is actually h over 2. It's half of our height. So we could use the Pythagorean theorem to relate h and r such that h over 2 squared plus r squared is equal to 10 squared, or 100. And h over 2 squared is h squared over 4 plus r squared equals 100. And we could either go ahead and plug in the, or solve this for h to plug in up here for the h, or if we prefer, we might notice that we've already got an r squared and we've already got an r squared. So we could just go right ahead and solve for r squared, saying that r squared is equal to 100 minus h squared over 4, or 1/4 h squared. And then go ahead and plug that into our volume equation, giving us the volume of this cylinder is pi h times 100 minus 1/4 h squared. And if you choose to solve for h instead, there's nothing wrong with that. But this will hopefully come out a little bit easier. And the next thing we need to do is we need to think a little bit about what our domain values are here. So we know that h can't be more than the total diameter of the sphere, and it's got to be more than 0. So h is going to have to be more than 0, but it's got to be less than 20, because the radius of the sphere is 10, so its diameter must be 20. So h has got to be some value between 0 and 20. So any critical values we get have to be between 0 and 20 if they're going to be considered. So let's go ahead and move on to the next page and write out our volume. And then we should, from there, be able to take its derivative. So if I distributed that through, we had pi h times 100. So that's just going to be 100 pi h. And then we had pi h times 1/4 h squared. There was a minus in between. So that's going to be 1 minus 1/4 pi, or pi over 4 h cubed. And when we go ahead and take that derivative, the prime is going to just be 100 pi, because the h goes away, derivative of h is 1. And then minus 3 pi over 4 h squared. And we can see this is never going to equal 0, so I'll just kind of make a note. V prime is never undefined off to the side. But v prime does equal 0 if this equals 0. And so, well, that's going to look like 3 pi over 4 h squared equals 100 pi. Or if we multiply by 4 and divide by 3 pi, h squared is equal to 400 pi over 3 pi, or just 400 over 3. The pi's on it just cancel out. And square rooting this gives us h equals plus or minus 20 over root 3, but we'll only use the positive because we know that our domain only included values from 0. So when we make our sign chart, we'll put 0 and 20 on here as endpoints, and we'll throw 20 over root 3 in there. And of course, it might be helpful for us to know what 20 over root 3 is approximately, just to help us with the sign chart. So if we go into our calculator, we can see that 20 over the square root of 3 is equal to 11.5 or so. So coming back to our work here, this is approximately 11.54700. 538. And I'm sure we must have had units. I don't remember what they were, so let's go back and look. Centimeters again. So we'll call these centimeters. So if we're going to plug something into our derivative here, it's less than 11. Let's go with something easy like 1. We plug in 1 here. We've got 100 pi minus 3 pi over 4. Now, clearly, 100 pi is more than 3 pi over 4. We end up with a positive value here, so our function is increasing. And if we put in something more than 11, like say 19, I think we could, 19 squared is 361. Right, so we get 361 times 3/4. We're going to do 361 times 3/4. That's going to be clearly way over 100. So we're going to have 100 pi minus something that's way more than 100 times pi. That's going to be a negative value and we'll be decreasing here. And so we can see that we are at a maximum when our height is about 11.54700538 centimeters, or 20 over root 3 centimeters. And the original question asked us for the volume, what is the maximum volume, and to find the dimensions of that cylinder. So to find the radius, we had R, in fact, I'm going to do this in a different color. We had R squared equals, right here, 100 minus 1/4 of h squared. So that will be R squared is equal to 100 minus 1/4 of 20 over root 3 squared, which is 400 thirds, which gives us R squared is 100 minus 100 thirds, which would be R squared equals 200 thirds, which if we simplify that down after we square root, R is going to be the square root of 200 over the square root of 3, which would be 10 root 2 over root 3 centimeters as well. So we've got that as our R value. We've got this, 20 over root 3, as our H value. And we can then put those together, pi R squared H, to find our volume itself. So we've got volume is, we have volume was equal to pi times our radius squared. Well, our radius squared was 200 thirds, times our height, which was 20 over root 3, which would be 200 times 20 is 4,000. So we've got 4,000 pi over 3 root 3 centimeters as our volume. And we're almost done here. We're just going to look at one more problem today. We've got a cylindrical metal container that is open at the top, so it does not have a top, kind of like our box in the first or second problem. And it's going to have a capacity of 24 pi cubic inches. Well, it's a capacity here. Capacity means it's volume. So our volume of our cylinder, I'm going to just kind of start putting some stuff out here. Volume of the cylinder is pi R squared H equals 24 pi. So we'll just keep that there and just think about that. And then we start studying about cost. The cost of the material for the bottom of the container is 15 cents a square inch. And the cost of the material for the curved part is 5 cents a square inch. And we're not wasting any material constructing it. We want to minimize the cost. Well, let's think about the surface area. The surface area is the area of the base, only one base because it's got no top, plus the area of the lateral piece. The area of the base, that's pi R squared. And the lateral surface area, as we talked about with the other problem, is just the circumference of the cylinder times the height, so plus 2 pi r h. Right? If we're talking about a open top cylinder, the base is a circle, its area is pi r squared, and our lateral surface area is the circumference, 2 pi r times the height. But we've got a little extra going on here, and that is the cost of the material is different for each piece. So the bottom of it costs 15 cents per square inch, and the lateral piece costs 5 cents per square inch. So all we really need to do here is write a cost equation. Cost is equal to, well, the surface area, or the area of the base part, times 15, because it costs 15 cents per square inch there. And then the curved part is its surface area, 2 pi r times h, times its cost, which is just 5, giving us an equation of 30, not 30, oops, 15 pi r squared plus 10 pi r h. But again, we can't have two variables, but it should be pretty straightforward. Since we already started with this, if we just divide both sides of that by pi r squared, we should solve for h. Divided by pi r squared here and here tells us that h is equal to 24 over r squared. So we can now go in and say that our cost is actually 15 pi r squared plus 10 pi r times 24 over r squared. And it looks like we're going to need a new page to finish this up. So we'll simplify that out here. Our cost is going to equal 15 pi r squared plus, well, we had 10 pi r times 24 over r squared. So that's going to be 240 pi. And we have r over r squared, which is r to the negative 1 pi. And now we are ready to take our derivative. Keeping in mind that r must be greater than 0, we're not going to have a radius of 0 or a negative radius. So when we take our derivative, c prime ought to be 30 pi r minus 240 pi r to the negative 2. And r to the negative 2 is, of course, r squared in the denominator. And if we get ourselves a common denominator here by multiplying by r squared and r squared in the numerator and the denominator, we'll end up with c prime is 30 pi r cubed minus 240 pi all over r squared. And, well, c prime is only undefined if r equals 0, but that's not in the domain that we just restricted ourselves to. R is greater than 0. So we're really only concerned about when the c prime equals 0. Set that numerator equal to 0. And we can then, we can just go ahead and solve that pretty straightforwardly. We'll add 240 pi, giving us 30 pi r cubed equals 240 pi. And when we divide by 30, and when we divide by pi, that's just going to give us r cubed is equal to 8, or our radius is 2. And of course, we'll want to make a sign chart to prove that this is a maximum or a minimum, prove which one it is. Or alternatively, if we wanted to, we could use a second derivative test, but I think it's probably just quicker here to throw 2 on a sign chart and say that, well, we can't have anything below 0. So if we plug in something less than 2, like 1, our denominator here is always positive. And our numerator, well, if r is 1, that's 30 pi minus 240 pi. 30 pi minus 240 pi is a negative number. So the function is decreasing. And something more than to like, I don't know, 10 or 3 or a million or whatever you might want that to be. If we plug that value in for r, let's say we use 5, r cubed is 125, and 125 times 30 is a lot more than 240. So when we subtract, we're going to get a positive telling us our function is increasing, and that our radius of 2 is giving us a minimum cost. And we'll look and see what the question was asking. It says what dimensions minimize the cost. And so our radius is going to be 2 inches. And we'll also note that the height was 24 over r squared. So this is a radius of 2 inches. And I'll note this over here was a minimum cost. And we also just said that our height was equal to 24 over r squared. Well, that would be 24 over 2 squared. 2 squared is 4. 24 over 4 is 6 inches. So a height of 6 inches with a radius of 2 inches ought to give us the minimum cost for this cylinder. And as we go through and do more optimization problems, you'll see that there's a whole huge variety of different types of optimization problems. And then some of them are pretty similar, they can be related to each other, but you do have to, at times, be creative in turning your function all in terms of one variable, oftentimes relating a volume or a surface area that's given. You might end up using similar triangles or the Pythagorean theorem, or any other number of formulas you've learned in the past to try and put your equations all into one variable. But that's going to be it with optimization. We only have one topic left in this application to the derivative unit, that's related rates, and we'll look at that next time.